Welcome to Chapter 6, Section 1, Definition and Existence of the Integral. With this episode, we open a brand new chapter and a brand new subject, integration. Chapter 5 was about the derivative. Now we build its partner, the integral, entirely from scratch. Rudin does something clever here. Instead of developing only the familiar Riemann integral, he immediately introduces a more general object, the Riemann-Stieltjes integral, in which a function f is integrated against a second monotonically increasing function alpha. The ordinary integral becomes the special case where alpha of x equals x. In this first section, we give the precise definitions, prove the basic machinery of refinements, establish the fundamental Cauchy-style criterion for integrability, and then use it to show that large classes of functions, continuous functions in particular, are integrable. Let's get started. Here's the plan for this episode. We begin with motivation. What problem the integral solves and why Rudin sets it up through upper and lower sums. Then come the two central definitions. Definition 6.1 constructs the Riemann integral from partitions, and definition 6.2 generalizes it to the Riemann-Stieltjes integral, where an increasing function alpha acts as a weight. Next, we develop the key technical tool, refinements of partitions, in theorems 6.4 and 6.5. The heart of the section is theorem 6.6, a criterion in the style of Cauchy that converts integrability into a concrete inequality, together with its companion, theorem 6.7. Finally, we harvest the consequences. Theorems 6.8 through 6.11 identify large classes of integrable functions. We close with a summary and a preview of the next episode. Let's set the stage. In Chapter 5, we developed differentiation, the local rate of change of a function. This chapter develops the other pillar of calculus, integration, which measures a total and accumulated quantity, such as the area under a graph. Throughout this chapter, we integrate real-valued functions over intervals. Complex and vector-valued functions follow in later sections, and integration over sets other than intervals must wait for chapters 10 and 11. Later in this chapter, the derivative and the integral will meet in the fundamental theorem of calculus. But first, the integral has to be defined with full precision. The construction Rudin chooses depends very explicitly on the order structure of the real line. Instead of taking limits of sums as the mesh of a partition shrinks, we will trap the integral between approximations from above and approximations from below, using suprema and infima, the tools we mastered in Chapter 1. This makes the theory clean and rigorous, with no new limit concepts at all. And here's the twist that gives the chapter its name. Almost for free, the same construction defines a more general integral, the Riemann-Stieltjes integral, written as the integral of f with respect to alpha. Here, alpha is a monotonically increasing function that acts as a weight, deciding how much each part of the interval counts. Taking alpha of x equal to x recovers the ordinary Riemann integral, so nothing is lost by generalizing, and, as we will see in the next episode, a great deal is gained. The central question of this section is the last line on the slide. For which functions EF does the integral actually exist? The construction will make sense for every bounded f, but its two halves, an estimate from above and an estimate from below, need not agree. The main theorems of this episode, theorems 6.8 through 6.11, give broad sufficient conditions for agreement. Before the formal definitions, Let's fix the geometric picture that drives everything. This picture is the whole section in one image. The blue curve is the graph of a bounded function, f, on the interval from a to b. We chop the interval into pieces using the partition points x sub 0 through x sub 4 on the horizontal axis. Over each piece, we build two rectangles, a green one whose height is the infimum of f on that piece, and a taller one reaching up to the supremum of f on that piece. The green area is the lower sum. It underestimates the area under the curve. The green and red together form the upper sum, an overestimate. The true area, whatever it is trapped between them, and the visible red band is exactly the gap between the two estimates. The legend on the right records this color code. Integrability will mean, by choosing the partition cleverly, the red band can be made as thin as we please. Now let's turn the picture into definitions. We start with definition 6.1. A partition of the interval from A to B is just a finite set of division points listed on the slide. The first point is A, the last point is B, and the points increase, or at least never decrease, in between. On the number line, you see a partition with 6 points, x sub 0 through x sub 5. The symbol delta x sub I denotes the length of subinterval number I, the distance from x sub I minus 1 to x sub I. The orange brace marks one of them, delta x sub 3. Notice that the subintervals may have completely different lengths. Nothing forces the partition to be uniform. Next, we use a partition to build the two sums from our opening picture. Now let f be a bounded real function on the interval. Boundedness is essential and will stay in force for the whole chapter. Given a partition, we look at f on each subinterval separately. On subinterval number I, capital M sub I is the supremum of the values of f, and lowercase m sub I is their infimum. Both exist as finite numbers precisely because f is bounded. This is the least upper bound property of the real numbers doing its job. These are the heights of the red and green rectangles from our picture. From them, we now build the two sums. The upper sum, capital U, of p and f adds up supremum times length over all subintervals. Each term, m sub I times delta x sub I, is the area of one tall rectangle. The lower sum, capital L, of p and f does the same with the infima, giving the total green area. Since on every subinterval the infimum is at most the supremum, the lower sum never exceeds the upper sum for the same partition. Every reasonable notion of area under the graph must land between these two numbers. That observation motivates the next definition. To get rid of the dependence on the particular partition, we now optimize over all of them. Equation 1 defines the upper Riemann integral of f, the infimum of all upper sums, the best possible overestimate. Equation 2 defines the lower Riemann integral, the supremum of all lower sums, the best possible underestimate. Note the direction of each optimization. Upper sums are pushed down, lower sums are pushed up, and the two bars over and under the integral signs record which is which. The obvious question is whether the two sides meet. If the upper and lower integrals are equal, we say that f is Riemann integrable on the interval, and we write f belongs to script r, where script r denotes the class of all Riemann integrable functions. The common value of equations 1 and 2 is then called the Riemann integral of f, written as in equation 3, or with the variable displayed as in equation 4. So the integral is not defined as a limit of Riemann sums. It is defined as the meeting point of an infimum and a supremum. Before asking when they meet, let's check that both quantities always make sense. Here is the promised sanity check. Because f is bounded, its values lie between two fixed numbers, lowercase m and capital M. On any subinterval, the infimum of f is then at least m, and the supremum is at most capital M. So the displayed chain of inequalities holds for every partition. Every lower sum is at least mem times the length of the interval, and every upper sum is at most capital M times that length. The sums therefore form a bounded set of real numbers, and the infimum in equation 1 and the supremum in equation 2 both exist. As the gray box says, the upper and lower integrals are defined for every bounded function without exception. Whether they are equal is the delicate question. To see how badly equality can fail, think of the function on the unit interval that equals 1 at every rational and 0 at every irrational. Every subinterval contains points of both kinds, so every upper sum is 1 and every lower sum is 0, no matter the partition. Instead of studying the question just for the Riemann integral, Rudin immediately moves to a more general setting. Here is the generalization. Definition 6.2. We bring in a second function, alpha, which is monotonically increasing on the interval. Since its values at a and at b are finite, alpha is automatically bounded. Given a partition, delta alpha sub I denotes the increase of alpha across subinterval number I. Since alpha is increasing, these numbers are never negative. The diagram shows the idea. The blue curve is the graph of alpha. The two dashed lines project the subinterval endpoints, x sub I minus 1 and x sub I, up to the graph and across to the vertical axis. And the orange brace marks delta alpha sub I, the rise of alpha. Where the Riemann integral measured a subinterval by its length, we now measure it by how much alpha grows across it. Everything else is copied word for word, as we see next. Now replace length by the growth of alpha everywhere. The upper sum u of p, ef, alpha adds supremum times delta alpha sub I over the subintervals. The lower sum uses the infima with capital M sub I and lowercase m sub I, exactly as in definition 6.1, equations 5 and 6. Then define the upper and lower integrals of f with respect to alpha, the infimum of the upper sums and the supremum of the lower sums over all partitions just as before. The whole structure of definition 6.1 carries over with delta x, replaced by delta alpha. One more step gives the integral itself. If the upper and lower integrals with respect to alpha agree, their common value is written as in equation 7, or with the variable displayed as in equation 8. This number is the Riemann-Stieltjes integral, or simply the Stieltjes integral, of f with respect to alpha over the interval. When it exists, we say f is integrable with respect to alpha in the Riemann sense, and we write f belongs to script r of alpha. So for each increasing weight alpha, we get a whole class of integrable functions, and the membership question depends on both f and alpha. Two remarks before we move on. First, the ordinary Riemann integral really is a special case. Take alpha of x equal to x. Then the growth of alpha across a subinterval is just its length. Delta alpha sub I equals delta an x sub I, and definition 6.2 collapses to definition 6.1. So everything we prove about the Stieltjes integral automatically holds for the ordinary integral. Second, and this is worth emphasizing, the weight alpha need not be continuous. Jump functions, staircases, are perfectly legal weights, and later in the chapter they will let the Stieltjes integral swallow infinite series as a special case. That flexibility is the whole point of the generalization. Next, a short remark about notation. A few words about notation. Rudin prefers the bare form of equation 7 without the letter X, because the variable of integration is a dummy. It can be renamed at will. Writing the integral of f of y d alpha of y means exactly the same thing. The integral is a number determined by 4 pieces of data: the function f, the weight alpha, and the endpoints a and b. The slide shows the perfect analogy. A finite sum does not depend on whether its index is called I or k. Both symbols denote C sub 1 plus C sub 2 up to C sub n. Of course, no harm is done by inserting the variable, and sometimes it is convenient. Now we set our standing conventions and begin investigating existence. Before diving into theorems, we fix the standing assumptions, so that they do not have to be repeated in every statement. From now on, f is a real bounded function on the interval, and alpha is monotonically increasing on it, and when no misunderstanding is possible, the integral sign is written without its limits. The goal for the rest of this episode is on the slide: to decide when f belongs to script r of alpha. That is, when the upper and lower integrals meet. The key tool is the idea of refining a partition, which we develop now. Definition 6.3 introduces the key technical device of the section. A partition P* is a refinement of P if it contains every point of P and possibly more. We only add division points, never remove them. Given 2 partitions P sub 1 and P sub 2, their common refinement is simply their union, the partition containing the points of both. The diagram shows all 3 number lines. On top, P sub 1 with its blue points, in the middle, P sub 2 with its orange points, and at the bottom their union, where both families of points appear together. The common refinement is the coarsest partition that refines both. Why refine? Because refining always improves both of our estimates, as the next theorem shows. Theorem 6.4 says that refining a partition never hurts. Inequality 9. The lower sum computed with the finer partition, P* is at least the lower sum for P. Refining pushes lower sums up. Inequality 10. The upper sum for P* is at most the upper sum for P. Refining pulls upper sums down. Together, the trap around the would-be integral only tightens as we add division points. Intuitively, more points mean the rectangles can hug the graph more closely from both sides. The proof is a pleasant computation, and it is enough to understand what happens when we add a single point. To prove inequality 9, suppose first that P* contains just one extra point, call it X*, and say it falls strictly between the consecutive points x sub I minus 1 and x sub I of P. The old subinterval splits into 2 halves. Let W sub 1 be the infimum of f on the left half, and W sub 2 the infimum on the right half. The key observation is at the bottom of the block. Both W sub 1 and W sub 2 are at least M sub xi, the infimum over the whole subinterval. The reason is stated below the box. Shrinking the set over which we take an infimum can only raise the infimum, because there are fewer candidates competing to be small. Let's see this in a picture before computing. Here is the geometry. The blue curve is f on the subinterval from x sub I minus 1 to x sub I, and the orange point x star is the new division point in the middle. Before refining, the lower sum used one flat rectangle over the whole subinterval. At the height m sub I, the overall infimum, that is the light green slab. In this picture, SF dips lowest in the right half, so the right infimum w sub 2 coincides with m sub I. But on the left half, the function stays high, so the left infimum w sub 1 is strictly larger, and the lower rectangle over the left half can rise to that level. The darker green block is precisely the area gained by the lower sum when the point x star is added. The upper sums behave symmetrically. Refinement lets the tall rectangles come down. Now we compute the gain exactly. Now the computation. All terms of the two lower sums agree except those coming from the split subinterval, so the difference of the lower sums is exactly what is displayed. The left half contributes w sub 1 times the rise of alpha over the left half. The right half contributes w sub 2 times the rise over the right half, and we subtract the old term m sub I times the rise over the whole subinterval. In the second line, the old term is split across the two halves, and the difference is regrouped into two products. Each product is non-negative. The first factors are non-negative because w sub 1 and w sub 2 are at least m sub I, and the second factors are non-negative because alpha is increasing, so the gain is at least 0, which is inequality 9 for one extra point. The general case follows by iteration. If the refinement p star has k extra points, insert them one at a time. Each insertion is the situation we just analyzed, so each insertion can only increase the lower sum, and after k, steps inequality 9 is proved. The companion inequality 10 for upper sums is proved the same way, with suprema in place of infima. There, splitting a subinterval can only lower the supremum on the two halves, so the upper sum comes down. The technique is worth noting. Reduce to the smallest possible change. One added point, then iterate. With theorem 6.4 in hand, we can compare the lower and upper integrals themselves. Theorem 6.5 states what the notation has been suggesting all along. The lower integral is at most the upper integral. Let me stress that this is not automatic. For a single partition, we know the lower sum is at most the upper sum, but the lower integral is a supremum over all partitions, and the upper integral is an infimum over all partitions. So we must compare the lower sum for one partition with the upper sum for a completely different one. The common refinement is exactly the bridge between two unrelated partitions, and the proof is a one-line chain of inequalities. Let's see it. Given two arbitrary partitions, p sub 1 and p sub 2, let p star be their common refinement. Now read the chain on the slide. The first inequality is theorem 6.4. Refining raises lower sums. The middle inequality holds because for the single partition, p star, the lower sum is at most the upper sum. The last is theorem 6.4 again. Refining lowers upper sums. The ends of the chain give inequality 11. Every lower sum is at most every upper sum, no matter how unrelated the two partitions are. Now, optimize. Fixing p sub 2 and taking the supremum over all p sub 1, the left side becomes the lower integral. That is inequality 12. Then taking the infimum over all p sub 2 turns the right side into the upper integral, and the theorem is proved. The trap is now fully set up, and we can ask when it closes. Here is the heart of the section, theorem 6.6. It says f is integrable with respect to alpha if and only if, for every positive epsilon, some partition P satisfies inequality. 13. Its upper sum and lower sum differ by less than epsilon. Think of it as a Cauchy criterion for integrals. Exactly as a Cauchy sequence is one whose terms squeeze together without knowing the limit, condition 13 certifies integrability without computing either the upper or the lower integral. In the language of our opening picture, integrability means the red band, the gap between the upper and lower rectangles, can be made as thin as we like by a single well-chosen partition. Nearly every integrability proof in this chapter goes through this criterion. Let's prove both directions. First, suppose condition 13 can be satisfied for every epsilon. The chain at the top holds for any partition whatsoever. The lower sum is at most the lower integral. Since that integral is a supremum of lower sums, the lower integral is at most the upper integral by theorem 6.5, and the upper integral, being an infimum of upper sums, is at most the upper sum. So both integrals are squeezed inside the same interval of length less than epsilon, and their difference, which is non-negative, is less than epsilon. Since epsilon was arbitrary, the difference must be 0. The two integrals agree, which is exactly the definition of f belonging to script r of alpha. Now the converse. Conversely, suppose f is integrable, and let epsilon be given. The integral is simultaneously the supremum of all lower sums and the infimum of all upper sums. By the approximation property of the infimum, some partition P sub 2 has its upper sum within epsilon over 2 above the integral, that is inequality 14. By the approximation property of the supremum, some partition P sub 1 has its lower sum within epsilon over 2 below the integral, that is inequality 15. The familiar difficulty appears again. These are two different partitions, and condition 13 needs a single one. The fix is the one we already know. Pass to the common refinement, which is at least as good as each of them. Let P be the common refinement of P sub 1 and P sub 2, and follow the chain. First, U of P is at most U of P sub 2, because refining lowers upper sums. Next, by inequality 14, U of P sub 2 is less than the integral plus epsilon over 2. Next, by inequality 15, the integral is less than the lower sum of P sub 1 plus epsilon over 2, adding epsilon over 2 to both sides. The integral plus epsilon over 2 is less than L of P sub 1 plus epsilon. Finally, L of P sub 1 is at most L of P, because refining raises lower sums. Reading the two ends, the upper sum of P exceeds its lower sum by less than epsilon, which is condition 13 for the single partition P. The criterion is proved, and we now record three useful companions. Theorem 6.7 collects three facts that make the criterion practical to use. Part A. Once a partition satisfies condition 13, every refinement of it satisfies condition 13 with the same epsilon. Good partitions stay good when refined, so we are always free to add extra points, for instance, to include some special point we care about, without spoiling the estimate. Next, Part B tells us what condition 13 says about values of f sampled inside the sub-intervals. Part B. Suppose condition 13 holds for a partition, and in each sub-interval pick two sample points, S sub I and T sub I, completely arbitrarily. Then the sum of the differences of the sampled values in absolute value weighted by delta alpha sub I is still less than epsilon. In words, on a good partition, f cannot oscillate much within the sub-intervals, on average with respect to the weight alpha. Finally, part C connects all this to the sums one actually computes in practice. Part C, if f is integrable and the partition satisfies condition 13, then any Riemann-Stieltjes sum formed by sampling f at arbitrary points t sub I and weighting by delta alpha sub I approximates the integral to within epsilon. This is the bridge between our definition through suprema and infima, and the familiar picture of the integral as a limit of sums of sampled values. It is also the form in which the criterion gets used for numerical approximation. The proofs of all three parts are short. Let's go through them. Part A is immediate from theorem 6.4. Passing to a refinement, the upper sum can only shrink and the lower sum can only grow, so their difference can only shrink, and if it was below epsilon, it stays below epsilon. For part B, look at one subinterval. Both sampled values, f of s sub ei and f only of t sub I, lie between the infimum m sub I and the supremum m sub di of f there, so their difference is at most m sub I minus m sub I in absolute value. Multiplying by delta alpha sub I and summing over I, the left side is at most the sum of the oscillations times the weights, which is exactly u minus L, and that is less than epsilon by hypothesis. One part remains. Part C is a squeeze, since each sampled value lies between m sub I and m sub I. The Riemann-Stieltjes sum, built from the points t sub I, lies between the lower sum and the upper sum. The integral also lies between the lower and upper sums, since the lower sum is at most the lower integral, and the upper sum is at least the upper integral. So the sum and the integral are two numbers trapped in the same interval, whose length u minus L is less than epsilon. Hence, they differ by less than epsilon. This completes theorem 6.7. With the machinery ready, we can now answer the big question: which functions are integrable? Here's the first and most important payoff. Every continuous function on the interval is integrable with respect to every increasing alpha. The strategy is on the slide. Continuity on a compact interval upgrades itself to uniform continuity. That was theorem 419, and it is precisely where compactness of the closed bounded interval enters. Uniform continuity means we can force the oscillation of f, the gap between m sub I and m sub I, to be small on every subinterval of a sufficiently fine partition, with one single delta working everywhere. Then the difference u minus L becomes a small number times a telescoping sum of delta alphas. Let's carry it out. Let epsilon be given. We first calibrate a small number eta. Since the total growth of alpha, alpha of b minus alpha of a, is a fixed finite number, we can pick eta so small that this growth times eta is less than epsilon. Note the wrinkle compared to the plain Riemann case. The target for ETA depends on alpha. Then, because f is continuous on the compact interval, theorem 4.19 makes it uniformly continuous, so there is a single delta such that inequality 16 holds. Any 2 points of the interval closer than delta have values closer than ETA. This delta works uniformly across the whole interval, which is exactly what a partition argument needs. Now take any partition, all of whose subintervals are shorter than delta. On one subinterval, any 2 points are within delta, so by inequality, 16 their values differ by less than ETA. Since f is continuous on the closed subinterval, it attains its supremum and infimum there. So the oscillation m sub I minus an m sub I is at most eta. That is inequality 17. Then compute U minus L is the sum of the oscillations times the delta alphas, which is at most eta times the sum of all delta alphas, and that sum telescopes. Consecutive terms cancel, leaving alpha of B minus alpha of A. By our calibration of ETA, the product is less than epsilon, so theorem 6.6 applies. Continuous functions are integrable with respect to every increasing weight. Next, monotonic functions. Theorem 6.9 handles a second large class, monotonic functions. Note the elegant trade of hypotheses. A monotonic f may have jump discontinuities, in fact countably many, as we saw in Chapter 4. The price is that the weight alpha is now assumed continuous, in addition to increasing. Some such assumption is needed. As we will see shortly, trouble arises exactly when f and alpha try to jump at the same point. The proof introduces a genuinely new trick. Instead of making the subintervals short in length, we choose the partition so that alpha grows by the same amount on each subinterval, and then let the telescoping happen on the side of f. Fix epsilon and let n be a large positive integer, to be chosen at the end. We build a partition adapted to alpha rather than to length. Each subinterval should carry exactly the same share of the growth of alpha, namely alpha of B minus alpha of A divided by n. Why does such a partition exist? Because alpha is continuous and increasing, the intermediate value theorem, theorem 423, says alpha takes every value between alpha of A and alpha of B. So we can pick x sub 1 at the point where alpha has completed the first of n equal shares of its total climb, x sub 2 where it has completed 2 shares, and so on. This is the only place continuity of alpha is used, and without it, the argument would break down. Suppose f is monotonically increasing. The decreasing case is analogous. On each subinterval, an increasing function attains its supremum at the right endpoint and its infimum at the left endpoint. So m sub I is f of x sub I, and m sub I is f of x sub I minus 1. No suprema or infima to estimate. We know them exactly. Now compute u minus L. Every delta alpha equals the common value, so it factors out of the sum, and what remains is the sum of f of x sub I minus f of x sub I minus 1, which telescopes to f of b minus f of a. So the difference is a fixed number divided by n, and taking n large enough makes it less than epsilon. Theorem 6.6 finishes the proof. Notice the symmetry with theorem 6.8. There the telescoping happened in alpha. Here it happens in f. Theorem 6.10 pushes beyond continuity. F may now have finitely many discontinuities, provided alpha is continuous at each of those bad points. The strategy is quarantine. We will enclose the finitely many bad points in tiny intervals chosen so that alpha grows almost not at all across them. Continuity of alpha at those points is what makes such intervals available. Off the quarantine zone, f lives on a compact set where it is continuous, hence uniformly continuous, and the argument of theorem 6.8 applies. The two contributions to u minus L's are then estimated separately. Let's set it up. Let epsilon be given. Let capital M be the supremum of the absolute value of f, and let E be the finite set of points where f is discontinuous. On the number line, the red dots are the bad points, and the orange segments around them are the quarantine intervals, u sub j to v sub j. Because alpha is continuous at each bad point, the growth of alpha across a small enough interval around that point is as small as we please. so we can arrange that the total growth of alpha over all the orange intervals is less than epsilon. We also place them so the intervals are disjoint, and every bad point away from the endpoints lies in the interior of the interval that covers it. Now look at what remains. Remove the open quarantine segments from the interval. What remains, call it K, is a closed and bounded subset of the real line, closed because we removed open segments from a closed interval, bounded trivially, so K is compact by the Heine-Borel theorem. Every discontinuity of F is interior to some removed segment, so F restricted to K is continuous, and continuity on a compact set upgrades to uniform continuity, exactly as in Theorem 6.8. There is one delta such that values of F at points of K closer than delta differ by less than epsilon. The stage is set. Now we build the partition. Build the partition as follows. Include every left endpoint, U, sub j, and every right endpoint, V, sub j, of the quarantine intervals, put no points inside them, and chop everything outside into pieces shorter than delta. Now estimate the oscillations. Every oscillation is at most 2 times capital M, since all values of F lie between minus M and M. This crude bound is used on the quarantine subintervals whose delta alphas add up to less than epsilon. Every other subinterval lies in the good set K and is shorter than delta, so its oscillation is at most epsilon. Those weights add up to at most the total growth of alpha. Adding the two contributions gives the displayed bound. The growth of alpha times epsilon plus 2m epsilon. Since epsilon was arbitrary, Theorem 6.6 gives integrability. A warning closes this circle of ideas. The hypothesis in Theorem 6.10 that alpha is continuous wherever f jumps is not an artifact of the proof. If f and alpha jump at the same point, integrability can genuinely fail. Exercise 3 of this chapter constructs the example with a step function integrated against another step function jumping at the same place. There the upper sums and lower sums stay a fixed distance apart no matter how fine the partition. The moral is on the slide. The theorems of this section are a balancing act between the two players. At any given point, at most, one of f and alpha is allowed to jump. One theorem remains, and it is a powerful factory for new integrable functions. The last theorem of the section, Theorem 6.11, is a machine for producing new integrable functions from old ones. Suppose f is integrable with respect to alpha, and its values lie in the closed interval from m to capital M. Let phi be any continuous function on that interval, and let h be the composition. H of x equals phi of f of x. The claim, h is integrable too. The examples on the slide show why we care. Taking phi of t equal to t squared shows. The square of an integrable function is integrable, and phi of t equal to the absolute value of t handles absolute values. In the next section, these two facts yield that products of integrable functions are integrable. The proof is the most delicate of the section, so let's first fix the strategy. Here is the plan. We must verify the criterion for h, knowing it for f. First, phi is continuous on a compact interval, hence uniformly continuous. A delta controls how much phi can spread values. Second, and this is the clever move, we choose a partition for f whose gap u minus L is less than delta squared, not just delta. Keep an eye on that exponent. Third, we sort the subintervals into two classes, class A, where f oscillates less than delta, and class B, where it oscillates by delta or more. On class A subintervals, uniform continuity of phi keeps the oscillation of h small. On class B, we only have a crude bound, but the delta squared budget will force the total alpha weight of class B to be tiny. Let's execute. Choose epsilon. Since phi is continuous on the compact interval from M to capital M, it is uniformly continuous there, so there is a delta, which we may also take smaller than epsilon, such that whenever two inputs differ by at most delta, the outputs of phi differ by less than epsilon. Since AF is integrable, Theorem 6.6 provides a partition P satisfying inequality. 18. The gap for F is less than delta squared. We are entitled to demand delta squared instead of epsilon, because the criterion works for every positive tolerance, and delta squared is just another positive number. Now, the class division. Write M sub I star and M sub I star for the supremum and infimum of H on subinterval number I, keeping the unstarred letters for F. Sort the indices. I goes to class A if the oscillation of F there is less than delta, and to class B if it is at least delta. On a class A subinterval, any two values of A differ by less than delta. So by our choice of delta, the corresponding values of H, which are phi applied to values of F, differ by less than epsilon. Hence the oscillation of H is at most epsilon. On a class B subinterval, we settle for the trivial bound. All values of H lie between minus k and k, where k is the supremum of the absolute value of phi, so the oscillation is at most 2k. The next step shows class B is small in the only sense that matters. Here is where delta squared pays off. On each class B subinterval, the oscillation of F is at least delta by the very definition of class B, so delta times the total alpha weight of class B is at most the sum over B of oscillation times weight, which is at most the full sum U minus L, and that is less than delta squared by inequality 18. This is inequality 19. Dividing by delta, the boxed conclusion appears. The total alpha weight of the bad class is less than delta. This is the same style of argument as the Chebyshev inequality in probability. Where the oscillation is large, the weight must be small, or the total budget would be exceeded. As the last line says, one factor of delta pays for the height of the bad rectangles, the other for their width. Now we assemble the estimate. Split U minus L for H into the class A part and the class B part. Over class A, each oscillation of H is at most epsilon, and the weights add up to at most the total growth of alpha. That gives the first term. Over class B, each oscillation is at most 2k, and by the boxed estimate, the weights add up to less than delta. That gives the second term, 2k delta. Finally, recall we arranged delta less than epsilon, so the whole bound is less than epsilon, times the bracketed constant, the growth of alpha plus 2k. That constant is fixed, and epsilon was arbitrary, so the criterion of Theorem 6.6 is met, and H is integrable. Composition with a continuous function preserves integrability. We close the theory with the natural question raised by this string of results. Exactly which functions are Riemann integrable? We have sufficient conditions, continuity, monotonicity, finitely many discontinuities, compositions, but no exact characterization. Rudin points ahead to Theorem 1133 Part B at the very end of the book. The answer, due to Lebesgue, is remarkably clean. A bounded function is Riemann integrable if, and only if, its set of discontinuities is negligible in a precise sense, namely, has measure 0. Making sense of that requires the measure theory of Chapter 11. So for now, we treat it as a preview of coming attractions. Let's summarize the episode. Let's review what we covered. First, the definitions. A partition chops the interval into finitely many pieces. The supremum and infimum of f on each piece generate the upper and lower sums, and optimizing over all partitions gives the upper and lower integrals, which always exist for bounded f and always sit in the right order. Integrability means they coincide, and the same construction with the length delta x sub I, replaced by the growth delta alpha sub I of an increasing weight function, defines the Riemann-Stieltjes integral. Choosing alpha of x equal to x recovers the ordinary Riemann integral as a special case. Second, the machinery. Theorem 6.4. Refining a partition raises lower sums and lowers upper sums, so the trap only tightens. Via the common refinement, this gave Theorem 6.5. The lower integral never exceeds the upper one. The workhorse is Theorem 6.6, the Cauchy-style criterion. Integrability is equivalent to finding, for each epsilon, a single partition whose upper and lower sums differ by less than epsilon. Theorem 6.7 added the practical consequences. Good partitions stay good under refinement, and Riemann-Stieltjes sums built from arbitrary sample points approximate the integral to within epsilon. Third, the harvest, who is integrable. Continuous functions always are, by uniform continuity. Theorem 6.8. Monotonic functions are, provided alpha is continuous. Theorem 6.9. Bounded functions with finitely many discontinuities are, provided alpha is continuous at each of those points. Theorem 6.10, and we saw that shared jumps genuinely destroy integrability. Finally, Theorem 6.11, composing an integrable function with a continuous one preserves integrability. The delta squared argument. In the next episode, we develop the properties of the integral, linearity, behavior under products and absolute values, splitting the interval, and the beautiful step function weights that make an infinite series literally a Stieltjes integral. See you there.